This is a nice follow-up to the paper we just looked at on producing hydrogen directly from seawater. This one is titled Kilowatt Scale Solar Hydrogen Production System using a concentrated integrated photoelectrochemical device. So photovoltaic and electrochemical devices are integrated to use concentrated solar power to produce electricity at kilowatt scale and also co-produces heat, as we will see in a minute. Reading the abstract, the production of synthetic fuels and chemicals from solar energy and abundant reagents offers a promising pathway to a sustainable fuel economy and chemical industry, which is a very optimistic view. We need safe, scalable, carbon neutral or carbon negative systems, of course, for net zero and decarbonization of the system. For the production of hydrogen, photoelectrochemical or integrated photovoltaic and electrolysis devices have demonstrated outstanding performance at the lab scale, but there remains a lack of larger scale on-sun demonstrations at greater than 100 watts. So kilowatt scale is here the example shown as functional in this method. Here we present the successful scaling of a thermally integrated photoelectrochemical device utilizing concentrated solar radiation to a kilowatt scale pilot plant capable of cogeneration of hydrogen and heat. A solar to hydrogen device level efficiency of greater than 20% at an H2 production rate of greater than 2 kilowatt or greater than 0.8 gram per minute, so that's the flux, is achieved. A validated model-based optimization highlights the dominant energetic losses and predicts straightforward strategies to improve the system level efficiency of greater than 5.5% towards the device level efficiency. We identify solutions to the key technological challenges, control and operation strategies, and discuss the future outlook of this emerging technology. I'm going to give it a very brief introduction. So here is the nice integrated system with the reactor here, solar concentration disk, CSP, the concentrated solar power kind of solar energy production as opposed to photovoltaic is being used in many places like Spain. There are advantages and disadvantages that you can read about and have podcasts elsewhere. So you can see the system has various details. I won't go into all of that. Main water supply, solar dish, electrical cabinet. There is a person at scale to tell you how big this system is. Main electricity supply, storage cabinet, H2 emerging vent line, and you have the water tank here, O2 water separator, and H2 gas sensor. Main water pump here, control cabinet, and N2 storage cabinet. And the details of the second part here: solar dish reactor truss, reactor box, water cooled shield, homogenizer, and CPV concentrated photovoltaic module there. So this is the second half of the figure. So this is the overview of the system. We looked at the technical illustration of the overall site showing key components such as the solar parabolic concentrator or dish reactor and ancillary hardware and cabinets. In B, we looked at close-up of the integrated reactor showing the assembly of the shield, homogenizer, PV, and enclosure. In C here, we are looking at a simplified process and instrumentation diagram of the system showing materials and energy flows. The key input-output intermediate system streams are composed of the PV generated electrical work available for electrolysis, heat output from the heat exchanger, and the external work required for water pumping. W and Q stands for work and heat respectively, and sensors are denoted by a circle: temperature sensor, pressure sensor, hydrogen concentration sensor, and the photographs of the system are given in the supplemental. So here is the water receiving H2, H2O flowing into the global water pump, and H2O deionizers and filters. So H2 is being extracted here and moving through the system with temperature and pressure sensors. Here is the solar dish giving it energy concentrated making a homogenizer. This is the integrated device of photovoltaic and electrolysis system here, with the cathode and the anode, again with the temperature and pressure sensors along the way. So here you are back pressure regulator, so water separator again into H2O and H2. That's what is coming out of the system. And the exchanger removes the heat here and again goes to another water separator, separating H2 and O2 and giving the remaining H2O back to the water tank. Okay. Quickly, this is a Sankey diagram where the thickness of the arrows correspond to the magnitude of the quantity being shown. Sankey diagram showing the magnitude and routing of the energetic flows through the system. The type of energy is denoted by the arrow color. So we are looking at electrical, fuel, heat, light, and light plus heat. You can track the color code. Calculated from averaged data for 20th August 2020, so real life situation here, where reasonable estimates are outlined further in the supplementary information that you can look up. The external electricity used for auxiliary components at 0.58 kilowatt is neglected from this system. So you just have to track life cycle analysis kind of numbers, what's being given and what's being produced. Obviously you want net positive energy coming out, either as electricity or heat. Heat is not a waste if it can be used, right? So solar input, oversized solar dish producing 35.5 kilowatts for this particular day. This is renewable energy, so we don't count that as opposed to the external electricity. So dish optical losses are at 7.3 kilowatts. Shield plus homogenizer are producing 18.5 kilowatts being supplied to the PV, and the shield losses here shown 9.8 kilowatts essentially coming into the PV, of which PV heat and light losses are at half a kilowatt, and you have for H2 output 3.1 kilowatt going into the electrolyzer cell, of which heat output is half a kilowatt, so 2.6 kilowatt H2 output here, and 6.2 kilowatt is lost by or converted to heat by the PV, and the shield and homogenizer are producing process heat at 13.7 kilowatt. Together you get 13.9 kilowatt heat output, but you lose 6 kilowatts here. So you can see the light and heat coming out in here and fuel coming out in here, and this is the kilowatt scale we're talking about. So purely solar driven with some external input which is too small and ignored, and they do some modeling to look at sensitivity analysis of water flow rate and power fuel at kilowatts and power of heat at kilowatts. So you can see as the water flow rate increases, the actual power fuel drops and the power heat increases. So there is an optimal number here where they cross. So you can read the details in the model, in the paper on the model, and the reasons for why you have such step drop or step rise from power fuel to heat, for example. Simulations and parametric analysis of fuel, power and heat separator. A to D are simulations of the effect of various parameters on the output fuel power and heat power. Effect of global water flow rate here. Effect of number of electrolyzer units here. NEC. Effect of the fraction of solar power received by the PV module and scaling PV area accordingly here. And effect of improvements in light homogeneity for all the dotted lines indicate the original values from the experimental demonstration. Okay, so there are losses involved which crash the system here in terms of power fuel production and convert it almost all to power heat here as you increase the number of electrolyzer cells. So there is an optimum number. This is not optimum here, but that's where the results are shown. So sorry about that. Looking at the increasing PV capture area, you again drop the heat conversion to heat and increase the power fuel, which is good news. Okay, so you can see the kilowatt here and kilowatt here for both. And here looking at linear interpolation of homogeneity, 0 is the actual experiment where it's done, 100% is the fully homogeneous light, and as you homogenize the light, the system becomes more and more efficient for producing power fuel, and the conversion to heat is dropped here to much lower levels. But keep the numbers here. These are going from 13.7 to 14, and here going from 2.5 to 3. In all these figures, the power heat is much larger than power fuel in terms of hydrogen. Okay, reading some bit of the conclusion, using the validated model, a parameter study is used to investigate promising optimization pathways, where key results are shown in figure 7, which we just looked at here. So I wanted to give a little bit of sense of the model used. First, increasing the water flow rate leads to marginally lower fuel power due to reduced short circuit current. Gradient is given here, and increased heat output power as piping heat losses are reduced. So I won't read all the numbers. However, with correspondingly colder output temperatures, so you have output power, the heat loss is reduced, but the resulting heat is also coming at lower temperature. Secondly, this analysis demonstrates that increasing the fraction of solar power received by the PV module and scaling the PV area accordingly, that is improved matching of dish power to the PV power, and improving light homogeneity, could substantially improve output fuel power at 0.09 kilowatt hour 0.09 per kilowatt hour percentage and 0.004 per kilowatt hour respectively, okay, while leading to a comparatively smaller decrease in output of heat power. Finally, in the present configuration, increasing the number of electrolyzer cells in the stack would only moderately improve the hydrogen production power, as it is limited by the light inhomogeneity. This trend continues until 42 of number of electrolyzer cells, when the performance rapidly deteriorates due to the operating voltage exceeding the voltage at PV maximum power. Okay, so these are observed before as well, as this reference here says. So it's a rather brief introduction, but I wanted to include it because it's exciting new technology and is done in real world situation to show the amount of power and heat generated. The heat power generated is still large, but if it's used efficiently, there are combined heat and power units that are being used already and are much more efficient than just power units or just heat units, which are typically used at grid scale or district level and so on. We've talked about that elsewhere. So just keep these in mind. I'm going to post these two together at some point. I keep on recording these and keep posting about 3 per week, not to overwhelm the audience, but hopefully I will keep catching up with the recording and posting. Okay, bye.